finally, to wrap up quantum configurations, they do relate a little bit to the periodic table, and there's a little bit of a shortcut you can use for reading and writing these, which makes it a little bit easier. So if we look at Nichols configuration, which we have right up here, and then we go to the periodic table that you guys have, and we want to see if this compares to our Bohr configuration. Nichols Bohr configuration is 2, 8, 16, 2. So we can kind of break this down. We've got our 2 electrons on the first one, 8 on the second, 16 on the third, and our 2 on the fourth. So, that does agree nicely with our Bohr configuration. And a lot of the time we just do use Bohr configurations. But you are responsible for being able to read and kind of decipher some of the quantum configurations. If you had to write all this out, there is actually a shortcut. You can actually use the noble gas core method, this is called. You select the noble gas that is directly behind your element. So that means it's going to be, if you think about this like a board game that you're progressing through by atomic number, this is going to be the preceding noble gas that you would find in group 18. Then you have to fill in the remaining orbitals using the periodic table as a guide and add up your subscripts to check your work. So your superscript, sorry. So you need to make sure you have enough electrons there. So we're going to actually do a shortcut for nickel. Nickel's preceding noble gas, so we're going backwards this way. So nickel's number 28. The noble gas before that, or the group 18 element before that, is argon. So it can be very confusing. It's definitely not krypton. Krypton comes after, so make sure you go backwards here. So our noble gas core is going to be argon, which we're going to write in a bracket. So all of these 18 electrons right here are the same, that's actually exactly the same thing as argon's configuration. So what we can write is we can say, okay, I'm going to write argon in brackets, then I'm going to write that 3d8 for S2 to show the, sorry, I'll make that look a little better, to show the remainder of my configuration. So what this tells me, if you're deciphering this, we're not going to write a ton of these, but you do need to be able to decipher them. So this is talking about 18 electrons, since argon has 18 electrons. 8 plus 2 is 10. So we're talking about 28 electrons here. So if this is a neutral atom, 28 electrons is referring to nickel. So you should be able to decipher them in that way. If you go on to college chemistry, you're going to write a lot more of these. You're going to really want to get familiar with this method. As far as valence electrons go, these are a little bit easier to determine using Bohr configurations. However, once you've written things in the noble gas core method, they're usually pretty easy done as well. So they're the outermost s or p orbitals. So if you look at sulfur's configuration, we have neon before that, and then these are our other electrons sticking out of there. That gives us 6 valence electrons, which makes sense with our Bohr configuration for sulfur, which is 2, 8, 6. So these are actually included in that neon, and then the other 6 are kind of just sticking out there. The periodic table does actually have a relationship to where electrons have last been put into an atom. And we'll get into this a little bit more later. It's just something I wanted to mention now. So this has to do with what type of orbital, s, p, d, or f, the last electron was added to. So this graphic of the periodic table shows anybody in what we call the s block right here had their last electron put in an s orbital. These guys all had their last electrons put in a p orbital. These guys are the d block. And then down here we have the f block, the purple f block. We don't deal with those guys quite as much. You can also see that by looking at the period, you can tell, what quantum number you should have with that as well. So period 1, 2, 3, 4, 5, 6, 7. So if you actually have to write these shortcut configurations, I'll show you what you're going to see in a college textbook. You're going to see this, okay? So I know it's a little bit blurry. You'll be able to read it a little bit better in your college textbook. It'll show you each of the elements, and then it'll show you their configuration. So it does make it a little bit easier to decipher them as you get used to reading them. But we can actually just use the regular periodic table to go ahead and write an element and write it in its shortcut. So I'm going to take a look at strontium. So I know you don't have this in your packet, but just to kind of show you what you're doing here. Strontium's right here. We want to look at the preceding noble gas. So strontium has 38 electrons. the preceding noble gas would be krypton. So what we're then going to do is we're going to write krypton in brackets. And that's representing, that's actually representing the first 36 electrons. We need to show 2 more. So you know you need to show 2 more, but you're like, I don't know where to put them because they didn't do Christmas tree. Are they in, the 1s, the 2s? Where the heck are they? So what this diagram can actually help us do, because strontium is in the 5th period, that tells us electrons are being put into the 5th, generally, except for in the D block, that's a little bit different, but we're probably looking at putting electrons into the 5th principal energy level. And because this is the S block, those electrons are going into the s orbitals. So this actually tells me pretty straightforward that's going to be 5s2. So that's kind of a simplified way to do that. Now, what you're responsible for is I should be able to give you this, and you should be able to tell me that it's strontium. So you should be able to say, okay, krypton's 36, plus 2 more electrons is 38, and 38 electrons in an atom, same as 38 protons, therefore I'm talking about strontium. And then if you go over to this handy-dandy chart you would have, you can see that right there, although it's a little bit blurry. So mostly these are for, the use of kind of identifying and making things a little bit shorter at the place you're at right now. What's interesting about this is when we learn a little bit more about behaviors of different elements, there are specific behaviors that elements have based on being in the SP or D blocks. So we'll learn a little bit more about that in our periodic table unit.